All right, our last big 30,000 foot view on a metabolic process deals with protein metabolism. And why we've sort of saved it to the end is proteins aren't really meant to be used as a fuel. And I know I've said this tons of times, but we're going to write it up top here. Proteins are meant to be building blocks. Okay, so proteins and their corresponding amino acids are meant to be building blocks. So what do we mean by building blocks? Well, they can either be made into other proteins. Remember that about half of your amino acids are what we consider essential. You cannot make them yourself, so you need to consume them in your diet. Probably a good point to sort of remind you of terms that we use a lot. I'll use the term necessary and I'll use the term efficient. There's lots of things that are necessary in your body. For example, glucose is necessary. You have to have glucose, but it's not essential because you can make it yourself. So we consider those 20 amino acids, about half of, all of them are necessary, but about half of them are essential, meaning you need to consume them in your diet because we do not have the ability to make them ourselves. Okay, so but there are times where maybe you have to get rid of excess proteins. Sometimes it's a protein turnover sort of situation in your body. Maybe you just did consume more protein than you needed in your diet and you do need to metabolize them. What we need to think about in that regard is the fact that there's an elemental problem, and that is said intentionally with amino acids. We have nitrogen. When we talk about our fuel equation, the products in our fuel equation are carbon dioxide, water, and energy, nothing that contains nitrogen. So if we draw and consider sort of an amino acid, right? Any generic amino acid has an amino group, has our carboxylic acid group. Our alpha carbon has a different R group. So what we have here is we have two unique parts. We have this elemental problem here in that we do not have in the crux of all the metabolic processes that we've talked about any way to deal with nitrogen. And then we've got the rest of this guy here. So this is our elemental problem. And how we deal with our elemental problem is the urea cycle. And we're actually not going to spend any time right now talking about the details of the urea cycle, but I will highlight that every single amino acid that needs to be metabolized, you literally are going to crack it in half. You're going to take the nitrogen and it's going to be handled in the urea cycle. Now, it's not as simple as that. We don't just break off that single atom, but we're going to sort of metabolize that nitrogen piece in the urea cycle. And then what I've got highlighted in blue here is what we refer to as an alpha keto acid skeleton. So alpha keto acid skeleton. So that's this blue part that we have here. And all of these alpha keto acid skeletons are going to be different based on the amino acid that they came from. Okay, so at its core, and you do not need to know anything about this picture right here, but when you take those alpha keto acid skeletons, they're going to resemble, I'm going to zoom in here just so that we can see this. We're not going to study any of this semester. We will next year. You can see that depending on what amino acid you are, you feed into metabolic processes, specifically the citric acid cycle, at different points. Here's the part that I need you to know. I need you to know that some amino acids resemble the branch point metabolite pyruvate, and then some of the amino acids resemble the branch point metabolite acetyl-CoA. Okay, so when we talk about sort of metabolizing these alpha keto acid skeletons, at its core, they're going to resemble either pyruvate or acetyl-CoA. Okay, so if they are resembling pyruvate, they can be converted into glucose. And we call those glucogenic amino acids. Okay, so glucogenic amino acids are amino acids that can be made into pyruvate. If you can be made into pyruvate, you can be made into glucose. Okay, if you are an amino acid that can be made into acetyl-CoA, here is the hydrophilic circulating fuel that you can be made into. You can be made into ketone bodies. All right, we talked about this a little bit in our we don't need to highlight that there. These are going to be called ketogenic amino acids. So again, any amino acid that can be made into acetyl-CoA can ultimately be made into ketone bodies, be metabolized and used by further degradation in the citric acid cycle. Now, here is the key, right? We've talked about this, that we cannot, and even though I drew that arrow, I need to quickly put my big red X there. Acetyl-CoA cannot be made into pyruvate, at least not in our metabolic systems, okay? We'll learn about this next semester. There are organisms that can convert acetyl-CoA into pyruvate, which means they can convert fats into glucose. We cannot do this. So I will say this 12 times from Sunday. We cannot do that process, which means fats cannot be made into glucose. So fats cannot be made into glucose. That is a super huge metabolic key that we need to think about. Okay, so how is this relevant? How does this tie into some of the other things that we've talked about? I want to take a second and talk about what happens if you are fasting. Okay, we're going to define what it means to be fasting. Okay, so fasting literally means no fuel consumption, no exogenous sources of calories. Okay, now if you are fasting, you still need to make sure that you are consuming water and any micronutrients that you might need. So that includes your vitamins and your minerals. We can't do biochemistry without salts, without vitamins, specifically our B vitamins. We've learned a lot about those. Okay, and one of the things that we know is if you are fasting, right, you are not consuming any endogenous sources of things. Exogenous sources of things. So particularly we need to make sure that we maintain 5 millimolar glucose. So critical, I cannot spell, critical to maintain that 5 millimolar glucose, right? That is key. And we've highlighted, right? Glucose is necessary but not essential. We need to make sure we maintain that 5 millimolar, but we don't need to get it from our diet. We can make it ourselves. So here's how this is going to happen, okay? We are going to take proteins and we're going to take glucogenic amino acids from those proteins, and we're going to do gluconeogenesis, and we're going to synthesize those into glucose, okay? So highlighting that this is a very costly process. So how are we going to pay that cost? Fats can pay this cost. So again, keep in mind what it means. If you're not consuming any fuels, okay, everything has to come from internal stores. Well, initially glucose, and we can fix that 5 millimolar glucose during the first few hours of a fast, right? Because we've got glycogen reserves. Glycogen in your liver can be broken down into free glucose, exported out to your bloodstream. 12 hours, we've said, before you need to start shifting metabolic gears to do something else. All right, so then let's turn to what we have then. If we're not consuming anything from the external world, right? What do we have internally? We've got our adipose tissue, right? Our adipose tissue can pay the cost of doing this process. Now, proteins, again, we've got reserves, but they're sort of unintentional. Unintentional reserves. We do not want to be breaking apart our own body to cannibalize it to provide these amino acids, but that is what will happen. We'll get into these details more next semester, but the first two things that atrophy are your liver and your kidney. They sort of self-sacrifice to provide amino acids so that you can do gluconeogenesis and synthesize glucose, right? Your internal reserves of adipose tissue will provide ketone bodies for energy, but they'll also provide energy to do this gluconeogenesis. So this is what's going to happen during a fast. But I will highlight that this is also what happens if you do a ketogenic diet, right? Ketogenic diet means you're still consuming calories, you're still consuming fats and proteins, but you are eliminating carbohydrates. So when you eliminate carbohydrates, your glycogen reserves get depleted fairly quickly, and you still need to maintain that 5 millimolar glucose. So how do you do that? Well, ideally, you still have your fat reserves pay the cost of this process, but now dietary protein can provide the building blocks. You don't need to cannibalize your own body in order to do this process, right? So this is why these diets can be so helpful and lose weight quickly, is because you're able to sort of tap into those internal reserves to pay this cost. Now I'm going to highlight here a super important piece is you need to make sure that you are insulin sensitive, because if you are still insulin resistant, you have the ability to deposit into that adipose tissue bank but not make withdrawals. Insulin is such an important hormone for sort of maintaining all of this. But ketogenic diet means you are not putting carbohydrates from an exogenous source into your body, which means you shouldn't be increasing your insulin levels, which means you should be able to regain insulin sensitivity. Once you regain insulin sensitivity, you can tap into that adipose tissue bank, cash in some of those reserves to pay the cost to maintain that 5 millimolar blood sugar. Remembering you have to maintain 5 millimolar blood sugar. If that drops, that's fatal, right? But glucose is necessary, but not essential. You have the built-in machinery to be able to do this. So you might ask the question, well, go back to that fasting piece. How long can you fast? In theory, you could fast for a month, right? As long as you are consuming adequate water, micronutrients. Now, you're probably going to be pretty emaciated after that. If you're completely relying on your own internal reserves for this, you're going to have muscles atrophy. It's not going to be a good thing to sort of fast for that long. We'll talk about fasting more next semester and get into more of the biochemistry of it. But one of the reasons that many people, particularly as they get older, decide that fasting might not be a good metabolic strategy for them, even though it can facilitate processes like autophagy, which is sort of a spring cleaning, if you will. We'll talk about those details next semester. One of the downsides is that you do tend to have muscle mass loss. And we know as you get older, maintaining adequate muscle mass is so important for multiple reasons. Okay, and so fasting can actually tap into that in an unintended way. But protein metabolism, I don't know if I probably should have started out by going back to this slide and just reminding you where we've been. Maybe this is a good point to sort of like sum this up, right? We're at the very last point of everything that we've sort of learned here. But again, highlighting proteins can sort of tap into this, either being glucogenic amino acids and converted to pyruvate. We've got ketogenic amino acids being converted into acetyl-CoA. Notice here how we deal with that elemental problem in the urea cycle. Wow. So that is the totality now of our 30,000 foot view. And we're going to move on now to understand how we regulate some of these important processes.